Both Einstein's theory of relativity and quantum mechanics are two of the most important theories in physics. But even though they were both developed within the first half of the 20th century, they are very different from each other. So what is the difference between relativity and quantum mechanics? Let's have a look. It helps to first clarify that there actually are two different theories of relativity. Einstein developed his special theory of relativity in 1905 and his general theory of relativity in 1915. The special theory deals with objects that move at constant velocity, so it doesn't have any acceleration. The general theory includes those cases, but also includes acceleration and gravity. It took Einstein 10 years to develop the general theory because he wanted it to be good. And indeed, it was and still is one of the most successful theories ever developed by humans. It's just incredible how well it fits with observations. And it also made some spectacular predictions that were later confirmed, such as the bending of light around massive objects or gravitational waves. Quantum mechanics, on the other hand, was developed by many people over a longer period of time in the late 1920s and early 1930s. Some of the key contributors include Max Born, Louis de Broglie, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and many others. It's a very different kind of theory. It's a statistical theory that assigns probabilities to predictions. It describes systems that are small enough so their quantum effects are important, such as atoms, photons, and electrons. The two theories together explain how the universe works from the very small to the very large. But there are some situations where they don't fit together easily, and that's where things get difficult. Let me mention three key differences between the two theories. First, the theory of relativity is deterministic. This means that if you know the present state of a system, then you can calculate exactly what will happen in the future. This is why we can, for example, calculate when the next solar eclipse will be. Quantum mechanics, on the other hand, is not deterministic. In quantum mechanics, you can only predict the probability of a certain outcome. You can't calculate what will happen in the future. This is why you can't say when a radioactive atom will decay, but only the probability per time that it will decay. The best way to understand this is to think of a coin. If you flip a fair coin once, you can't predict what the outcome will be. But if you flip the coin many times, then you expect half of the outcomes to be heads and half to be tails. Quantum mechanics is like this coin flip. It's inherently random. Second, the theory of relativity has no length or time scale. It can describe phenomena whether they are fast or slow, small or large. It's all relative, hence the name. Quantum mechanics, on the other hand, has a length scale and a time scale, and that's the size of the system. For example, the electron and Bohr's model of the atom is known to be in one of these orbits. You can't calculate the electron's position without knowing its size. That's because the electron is a quantum mechanical object. Here you see a schematic plot of how the wave function of an electron in an atom looks like. Wave functions are those funny, often weirdly-looking things that in quantum mechanics contain all the information about a system. This is one of the fundamental properties of quantum mechanics. And this is where the wave function is localized. Outside of this region, the probability of finding the electron is negligible. Now, if you want to know the probability of finding the electron in some region, you just need to integrate the square of the wave function over that region. If the region is very small, then the probability is also very small. If the region is very big, then the probability is close to 1. And third, and maybe most importantly, the theory of relativity treats gravity differently than quantum mechanics. In Einstein's theory of general relativity, gravity is described as a curvature of spacetime. This means that massive objects cause spacetime to curve and other objects roll along these curves. This is a beautiful theory and it works extremely well. In quantum mechanics, however, there is no such thing as space-time. Instead, there is space and time. They're different. Space and time are separate. And that means that a description of gravity in quantum mechanics is not a description of curved spaces, but it must be a force. The problem is now that the combination of a force and quantum mechanics leads to infinities. This is not just because we're bad at calculating, but it's a property of the mathematics. There are infinities in the mathematics of quantum electrodynamics and quantum chromodynamics. But in those cases, we can make sense of them. We just define the quantities that we measure to be the parts of the mathematics that don't have infinities. This procedure is called renormalization. But for a theory that combines gravity with quantum mechanics, renormalization doesn't work. At least we haven't figured out how to do it. This is the reason why physicists have been trying to find a theory of quantum gravity. A theory of quantum gravity should combine the two descriptions of gravity and quantum mechanics. This quantum theory of gravity would also explain what dark energy is, but it hasn't yet been done. One of the reasons that it hasn't been done is that we don't have any experimental evidence for quantum gravitational effects. This is because gravity is a very weak force compared to the other forces, so it only becomes important for very large distances or very heavy objects. This is why we don't notice these quantum effects. Another reason is that we don't have a good mathematical description of quantum gravity. Let me be clear that this doesn't mean that the current theories of gravity and quantum mechanics are wrong. They're not. They're two of the most successful theories we've ever had. It's just that there are some situations where they don't fit together nicely. This happens, for example, in the immediate vicinity of a black hole or in the early phases of the universe. It's in these extreme situations that a theory of quantum gravity is needed. And this is why we're looking for one. But even though we don't have a theory of quantum gravity, we have some ideas for what a quantum theory of gravity could look like. The best known proposal is probably string theory. String theory is an attempt to quantize gravity. It was developed in the 1970s and has since been worked on by hundreds of physicists. String theory says that the smallest possible length has a finite value. This smallest length is called the Planck length. The Planck length is incredibly small. It's about 10 to the minus 35 meters. The Planck length sets a lower limit to the length of everything. For example, if you try to quantize a string, you always end up with a minimum length of a Planck length. This is why it's called the Planck length. The Planck length is very small. It's about 10 to the minus 35 meters. The Planck length sets a lower limit to the length of everything. For example, if you try to quantize a string, you always end up with a minimum length of a Planck length. This is why it's called the Planck length. Now, string theory is highly speculative and controversial. Some physicists say it's nonsense and others say it's the future of physics. I personally tend to think that it'll turn out to be wrong, but I could be wrong. Maybe you'd like to make a research proposal for your summer holidays. In summary, quantum mechanics and the theory of relativity are two different kinds of theories that together explain the world around us. The theory of relativity is a deterministic theory that can describe everything from the very small to the very large. It has no length or time scale. Quantum mechanics is a statistical theory that describes systems that are small enough so that quantum effects are important. It's a theory that has a length and a time scale. Both theories together explain how the universe works. However, they don't fit together easily in all situations. This is why we're looking for a theory that unifies both theories. Thanks for watching. See you tomorrow.